Hello, everyone, and welcome back to your channel of Math and Engineering Made Easy. We are still working with vector fields, and today we are going to discuss a special type of vector fields that we call conservative vector field. So what is conservative vector fields? These are vector fields where if you place a particle and you apply the force that is conservative in this conservative field, the object will not experience rotation. So we can call it its irrotational field. Okay. And what happens then is that it makes the line integral easier to perform, as we will see probably next session or the next one. So I'm going to give you two examples, one in 2D and one in 3D, on how we find whether a field is a vector field is conservative or not. And then next time we'll take it a step further. So I don't want to make it a long lecture. So the first example, example one, I have a force given to me as 2xy cubed in the I direction plus, and then this one is 3x square y square plus, and we can have any function here of y, let's say sine y or something, or sine 2y even, it doesn't matter. So we are going to call the first term or the ith component m and the j's n. And if there is a kth, I'm going to call it p. And the check to see if this field is conservative or not, we say conservative field, meaning irrotational, if and only if partial m partial y equals partial n partial x. So I take the derivative of that with respect to y and the derivative of this with respect to x. If they are equal, meaning their difference is zero, another way to say it, partial m by partial y minus partial n by partial x equals zero. So let's see what is partial m by partial y. 2x becomes a constant. And then the derivative of y cubed with respect to y is 3y squared, meaning it's 6xy squared. Now, when we try to do partial n by partial x, 3y squared is a constant, and the derivative of x squared is 2x. And then this thing, that's what I said, any function of y would work, plus 0. 3 times 2 is 6xy squared. They are equal to each other, so that is a conservative field. When we go to the 3D, you have to check 6 things, like 3 pairs. M by y, n by x, m by z, p by x, n by z, and k or p by y. So it's a lot of work, right? So another way, a shortcut to do that, and it works both in 2D or 3D, is to use a determinant. To find the determinant where the top row is simply I, and this is wide, so let me give space. The second row is the del operator, partial, partial x, partial, partial y, and partial, partial z. And then the third one is your force. 2xy cubed, 3x squared y squared plus sine of 2y, and 0. If you know how to do it, it's so simple. If not, then we can use the duplicate column method that works with a 3 by 3 determinants, but only 3 by 3, not higher, not even lower. Lower is much easier, but like a 2 by 2, you can do it. 2xy cubed, 3x square y square plus sine of 2y. Now what we are going to do, like we learned, is to open a pair of brackets with a pair of parentheses in the middle. And between them, there is a negative sign. So we are going to take, well, I don't think I need the ruler, but just to show you, you should know that. I'm going to take the main diagonal and then the next one and the next one and add them, write them here. So plus, plus, plus. And then I go to the other diagonal. So I start with the K. And then the I, and then the J. And we are going to subtract these. And meaning I'm going to put them here. So the I times the partial with y of 0, which is 0. So you get 0i. And then for the j, you say partial z of 2xy cubed. There is no z. So plus 0j. But when you go to the k, you are going to take partial x of this thing, which is 6x y squared. Okay. Okay. Then when you go in the opposite direction, let's start with the I. Partial z of a function that only has x and y is 0i. Then the j, partial x of 0, so plus 0j. And then when you get the k, you get partial y. 3 times 2 is 6xy squared plus 6xy squared k. And you see 0 minus 0i, 0 minus 0j, 6xy squared minus 6xy squared, they cancel each other, so you get 0 vector. Of course, in 2D, it's easier to do it like that, but I was just giving you an introduction on what will happen if we have that in 3D. Let's take another example in 3D and check it out. So in this example, they tell you f equals y times z plus 2i plus xz plus 2x plus 4j plus xy plus 3k. And we want to check to see if this is a conservative field. So, like we did in the previous example, we are going to do a determinant. I, j again is wide. Oh, I put the j and k. And then I again and j. Partial x, partial y, partial z, partial x, and partial y. Z plus 2, xz plus 2x plus 4, xy plus 3, z plus 2, xz plus 2x plus 4. And again, these three, those three, those three. So let's start the first pair of parentheses. Partial y of xy plus 3 is simply x, so xi. then partial z of z plus 2 is 1, so plus j. Partial x of that, you get z plus 2, and that's the k, minus. And then I open the second pair of parentheses. And now I'm going to multiply these, and these, and subtract. I already subtract. So partial z of that is x plus 2. Oh, I'm sorry. That's partial y. So it's 0, but that's the k. Let's come here. Partial z of that, we said it's z plus 2. Z plus 2 I. And then partial x of xy plus 3 is uh partial x is y, so y j, right? And then finally partial y of z plus 2 plus 0k. And we can see from here that this one is not a conservative because neither the x nor the y nor the z component is 0. So not conservative. We were just checking to see whether it's conservative or not. Finally, we are going to take a third example, also in 3D. Let's take different color. Okay. F in this case is 12x square I plus cos y cos z j plus 1 minus sine y sine z k. And we want to see whether this is conservative or not. So I j k I j partial x partial y partial z partial x and partial y. 12x squared cos y cos z and 1 minus sine y sine z. 12x squared cos y cos the z. Okay. So in the first pair of parentheses, we'll do these three calculations. The derivative with respect to y here, notice it would be negative cos y sine z. And that's the I. When you go to the j, you get 0 because that's a derivative with respect to z of 12x squared, so plus 0j. And when you do the k, there is no x's, so you get partial x plus 0k minus. Then I go in the opposite direction. The derivative of z, I get negative. Cosine derivative of z is negative sine. So you get negative cos y sine z in the I direction. Then for the y, I'm sorry, yeah, for the j, it's a partial x of a function of y and z. So that's plus 0j. And then the derivative of y of that is plus 0k again. So you can see 0j minus 0j and 0k minus 0k. So these cancel. Here you get negative cos y sine z plus cos y sine z. They cancel each other and you get 0 vector. Hence, this is a conservative field. So the question is, what difference does it make? So why did you do all of that? That's what we are going to do next time. Only when a field is conservative, we can find something called its potential function. And the potential function makes the line integral very simple, as we will see. So next time we'll see, I'm going to use the same three examples. So we already seen them. So of course, the first and third, because the second one, we didn't get a conservative field, right? Remember, we didn't end up with zero vector. So we're going to take example one, it's a 2D. Example three is a 3D, and both are conserved. Thanks. Hope to see you soon. Bye.